All right, welcome back into Calculus 3. We are getting into defining equations of lines and planes, but we're going to start off with lines. Let's use a different color here. So equations of lines in 3 dimensions. Now, we can't just use a vector, right? If we use a vector, right, you'll see a graph show up over here. If we use a vector, it's just going to give us a direction, but remember we said 2 vectors are equivalent if they have, right, the same magnitude and the same direction, right? So that doesn't really give us a specific origin point or spot in a plane or space, right? So we actually need 2 things, right? For an equation of a line, we need a point. We'll define it as P, which is x naught, y naught, and z naught. And we also need a vector, which we will define as v, right? We'll say this is equal to a, b, and c. Okay, and again, so from our visual, what you're going to notice is we're going to take this point and we're actually going to turn it into a vector starting at the origin, right? So let's go ahead. We'll write this as r naught is going to be equal to the vector x naught, y naught, z naught. Right, so you can see from our visual, imagine we start off at the origin, we travel right to get to our point, so this vector is going to allow us to travel to our specific point that we want to get to, and then what we're going to do is we're going to define this line r equal to r naught. So this travels to the point of the line that's on the line, and then we want to move in the same direction as the line that we want. So it's plus some scalar t times our vector v. Right, and so t is just going to give us some scalar. If it's a positive value, will be to the right of r naught, and if it's some negative value, will be to the left of r naught. All right, well, let's try to examine this a little bit closer because we want to define x, y, and z parametrically, right? We want to parameterize them. So let's go ahead and we're going to expand this equation here just using everything that we have. So we're going to say r is equal to, instead of r naught, we'll write r vector plus t, I'll try to make it different than my plus sign there, times the vector a, b, and c. Right, and now we can start to define x, y, and z. So let's go ahead. We'll define x as equal to x naught plus the scalar t times a. And we can define, let's do y equal to the same thing, y naught, plus the scalar t times b. And I'm doing my best to make my t's and my plus signs look different. And lastly, z, right? Same idea. Z is equal to z naught plus t times c. Okay, so what's really happening here? We're stealing our starting positions, right? X naught, y naught, and z naught. And then we're stealing our direction vectors from our original vector, right? This vector is our direction vector, and we're just stealing the components here and carrying them over. The other form that we might see this in, let's go ahead and draw a line here, is what's called symmetric equations. And all we're going to do is we're going to solve each one of these things, right? These parametric equations for t. Now I'm only going to do one of them and you'll get the idea because the pattern will keep going. Say symmetric equations. So let's just go ahead, we'll deal with x for right now. So we'll say x is equal to, so we're just going to write this out again, x naught plus ta. And all I'm going to do, I'm just going to draw arrows to show what we're doing. We're going to move the x naught over. So we'll say x minus x naught is equal to ta. And we want to divide by a, right? So we have x minus x naught over A is equal to t. Okay, now what you can imagine is we can do this process, the same thing here for y and z, right? We could solve it equal to t. And you would see the same pattern would emerge, right? It'd be minus, right, our starting position, divided by the actual component of the direction vector. And so if all those things are equal to t, what do we end up with? Let's write it out. So t is equal to, and I'll just write out this one first, x minus x naught over a, which is equal to, same pattern here, y minus y naught over b, which is equal to, same pattern, z minus z naught over c. Right, so those are the different ways that you can see it. Again, equation of a line, we can't just use a vector, right, because that doesn't give us a physical location within space. We need a point and a vector, right? And then we go through this process of taking our point, turning it into a vector. That allows us to travel from the origin to our point, and then from there we can use vector addition and vector scalar multiplication, right, to travel along a specific line in space, right, in 3 dimensions. All right, so hopefully this helps. We'll go through some examples in the next part of the video, and I will see you shortly. All right, now let's take what we learned in the first part and we'll do some examples, right? So first example, we'll start off with an easy one, right? So we'll say we're gonna find the equation of a line, and I'm gonna give you a point. Let's say, so given, and we'll say point P, and let's go ahead and do -2, 4, and 5. And what I would do if I give you this information immediately, right, I'm going to walk through all the steps. Obviously, you can shortcut it once you see the pattern, but immediately what I'm going to do is I'm going to form my R naught vector. All right, so R naught is equal to -2, 4, and 5. And I need to give you a direction vector. We'll do 2, 5, and -3 equals 2, 5, and -3. And then most of us at this point, we can jump straight to, right, writing this out parametrically. I'll do it one step at a time, right? We want to define our line R. It's going to be equal to R naught, -2, 4, and 5, plus t times, I should maybe do this in a different color, 2, 5, -3. There we go. Right, so let's break this up parametrically into x, y, and z. So x is equal to, let's go ahead, we'll take our first component, -2, plus t times 2, and maybe we should have wrote it as 2t. We'll leave that for right now. Let's rewrite this. -2 plus 2t. There we go, that looks better. Y is equal to, we have 4, and we'll do plus 5t. And lastly, we have z is going to be equal to 5 minus 3t. Awesome. Okay, so this is our first example. Not too bad, right? I give you a point. We should see a visual over here. I give you a point. We can create this R naught vector. We are given a direction vector. That's all we need to write the equation of a line in 3 dimensions, and we have broken it down now parametrically into an x, y, and z. Right, so that's our first option. Right, but what about if I just immediately give you this? Right, so let's say over here, we'll draw a line. Right, so I'm going to give you a point. Let's go ahead, I'm going to say given point, and we'll do 4, 5, and -3. And I want us to construct a line that is going to be, let's say, parallel. So given this, and we want to be parallel to the following set of parametric equations. So parallel to, and let's write out the following set. We have x is equal to 4 minus 3t, The next one, y is equal to, we'll do -2 plus, we'll do 5t, and we'll say z is equal to 4 plus t. Awesome. Right, so we're given a point, and we want to be parallel to this line that we've defined parametrically. Now remember, right, so we're going back and forth here. How did we write this line? Well, if we want it to be parallel to this line, all we care about is the direction vector, right? I don't care about the point. So I go, okay, I want to be parallel to this line, meaning I want it to have the same direction. Well, what's our direction vector here? We'll just call this v. This is equal to just the slopes, right, of these parametric equations. So we have -3, 5, and 1, and guess what? Now again, we have a point, we have a direction vector, right? At this point, if you want to go through these steps, you can, but we can kind of skip some steps and just go straight to our parametric equations that we care about. So we're going to have x is equal to our point, so we'll say 4 minus 3t. Y is equal to our point, 5, plus 5t. And lastly, z is going to be equal to, what do we have for our point? -3, and we have plus t. Awesome. Right, so that is it. We have two options here that I've given us, right? Either I give you a point and I give you the vector, right, of the direction. In this case, I gave you a point and I said, let's be parallel to this other line, right? Well, that line has a direction, and that's all we care about. Parallel just means we have the same direction. So we're taking the direction vector out of this parametric system or parametric equations. We've rewritten it. We have our point. We have our vector. We can now construct our own parametric equations, and we're good. All right, so two different examples. I have more to come. We're going to tell the difference between skew, parallel, as well as orthogonal or perpendicular lines. So I will see you in the next example. All right, let's do one more example before we move on to planes. Actually, let's get rid of this color. We're going to define, right, what it means for lines to be parallel, intersecting, and skewed, and how can we see the difference between those three. And we're just going to go straight into an example here. Right, so if I give you two lines, I'm going to have us work a little bit on going back and forth between symmetric and parametric. Right, so I'll give you our first line. Let's define it as L1. And we're going to say this is going to have our three components. So we'll say T is equal to, and I'm just going to go with the symmetric equations here. And so let's say negative here. Right, the negative applies to the entire thing. X plus 4 over 3. And where this is going to be equal to, again, y minus 3 over 4, which is going to be equal to, we have negative z plus 4 over 3. So this is the first part. And at this point, we're just going to go straight into writing this in parametric form, right? So again, this negative sign applies to the whole thing, negative sign applies to the whole thing. So again, I'm solving for x, I'm solving for y, I'm solving for z. All of these things are equal to t. So what happens here is we'll have x is equal to, we'll move over the -3 and we'll move over the -4. So we have minus 4 minus 3t. We'll do y. The 4 comes over, the -3 goes over, so we're going to have y is equal to 3 plus 4t. And same thing. Z will be equal to, and notice that these two are the same, right? So it's going to be -4 minus 3t. Okay, so we have our first line. Now we have to do this same thing. So again, getting used to going between symmetric and parametric. let's go ahead. We'll define our next one. Now I'm going to write this as t, but we're going to switch this a little bit later on. So we'll say t is equal to, let's go ahead. We have negative x plus 5. The negative, I'll write it this way. It applies to the whole thing. I don't want to confuse people. Over 4. We have this is going to be equal to the negative, right, applies to the whole thing. Y plus 4 over 3. And we'll have negative z, so our negative z plus 3, sorry. My own writing is confusing me, over 2. Right, so again, the negatives are applying to the whole thing here. All of these are negatives. And so again, we'll go through the process of taking this and writing it parametrically. Now I'm going to make one quick switch. Just because we use t here as our scalar does not mean we have the same exact t down here in line 2. So even though I wrote it as t equals, we're going to use a different scalar s, right? Because they don't have to be the same scalar. So we end up with x is equal to, the negative 4 goes over, we have a minus 5. So minus 5 minus 4t. And same thing, y minus 4 to the other side, minus 3t. Oh, I wrote t, didn't I? Let's go with an s. Sorry guys, we'll go with s's. At least I caught it for that second one. And one more, right? So same thing, z minus 3. And then negative 2s. So again, I want to repeat, just to reiterate this, right? We're using this scalar t, right, to define the scalar of the line for that vector. But in this case, we're using s because they don't have to be the same scalar necessarily, okay? So the very first thing that we want to do is check to see if these two lines are parallel. That's option 1. If they're parallel, super nice, we're done. We're on to our next part of our question. Right, so let's go ahead. If they're parallel, they have the same direction vector, right? So let's go ahead and define L1's direction vector with V1, right? So V1 here is equal to the direction vector. Well, what is that, right? This, right, defines our direction vector. So we have negative 3, positive 4, and negative 3. And we'll do the same thing here with our L2. What do we have? Negative 4, negative 3, negative 2. So we'll say V2, right, our second direction vector, we have negative 4, negative 3, negative 2. And now what we would see if these were parallel is that V1 and V2 would be scalar multiples of each other. Or in other words, what we would see is that maybe V1 is equal to some scalar, we'll say k, times V2. And right, we can see that is not the case. Right, there's no scalar that I can multiply V1 to get V2 or vice versa. Right, so they are not parallel. Right, that's option 1. Okay, so we've crossed off option 1. We've moved on now to option 2. Option 2 is that they are intersecting. Right, so intersecting means that they have the same x, y, z value at a specific point, right? They have a point that intersects. So all I want to do is set these equations equal to each other. So let's go ahead and do that. I'll draw a line here. Okay, let's say, so our x minus 4 minus 3t should be equal to minus 5 minus 4s. All right, that is our first piece. We'll go with our next one, our y's. We have 3 plus 4t should be equal to our y down here, minus 4 minus 3s. And lastly, negative 4 minus 3t should be equal to negative 3 minus 2s. Okay. All right, so we've set up all of these inequalities, And now we want to substitute, right? So we're going to take our first equation here, right? We're going to take this equation and we're going to solve for t, right? So we end up with, I'll put a little bit of a line to show a separator. We're going to take this, solve for t. So we have negative 3t is equal to negative 5 plus 4 minus 4s. Right, and of course we can do that addition, or negative 5 plus 4 is negative 1, and divide by negative 3. So we have t is equal to negative 5 plus 4, negative 1 divided by negative 3, we have 1/3. And then negative 4s divided by negative 3 plus 4/3 s. Okay, so we've solved for t. And now what do we do once we've solved for t is we want to go substitute it into either one of these equations. Right? Well, I'm going to choose the easier one. So for substituting this in, these ugly fractions of thirds will help if I plug it into my last equation here because that is a 3. Right? So plugging it into my last equation, what do I get? So let's see. We have negative 4 minus 3, we're going to plug in t, 1/3 plus 4/3 s is equal to negative 3 minus 2s. And now we're going to simplify. Right, let's see what happens here. We have negative 4 minus 1 minus 4s is equal to negative 3 minus 2s. Now we want to solve for s's, move all the s's to one side, move everything else to the other side. So we have negative 5, we'll move this one this way. Negative 5 plus 3, we end up with negative 2. And if we move the 4s to the other side, we'll have positive 2s, which means s is equal to negative 1. Okay? So we're part of the way there. Right, now if s is equal to negative 1, right, let's go find out what must t be. Right, so if we plug s is equal to negative 1 into t, which is what we have here, we're going to end up, let's switch colors. And I'll review this. I know there's a lot of steps happening here. T is going to be equal to 1/3 plus 4/3 times negative 1. So negative 4/3, which will also be negative 1. Right, so now we have an s and a t. Right, they're both equal to negative 1. So guess what? These are indeed intersecting lines. There's going to be a value, right, that works. So let's go ahead and take this value and plug it in to either one of our line 1 or line 2, and it will give us the point that we intersect at. Right, so let's go ahead and check out and see if this is true. So let's plug it into, we'll do L1. Right, so I'm going to define a little space here, and we're going to figure out this point at which they intersect. Right, so in this case, x is equal to, we have negative 4 minus 3 times negative 1. And we have just enough space to write the answer. Negative 4 plus 3, negative 1. Perfect. We'll do the same thing now for y. We have y is equal to, we'll use the same y, it doesn't matter actually, 3 plus 4 times negative 1. What do we get? A negative 1. And lastly, z, right? We'll switch back and forth to color coordinate here. We have z is equal to negative 4, and this is the same as up here. Negative 4 minus 3 times negative 1, negative 1. So our point of intersection is at, I'll just say point of intersection is at -1, -1, -1. Right, so again, we can take our S value as well, which is -1, and go plug it into line 2 if we were so inclined, right, to double check our work and make sure this lines up. And maybe you'll do a quick check, right? -5 plus 4, -1, -4 plus 3, -1, -3 plus 2, -1. So indeed, our point of intersection, right, -1, -1, -1. Right, now again, our three options are parallel. We cross that off our list. Right, intersecting, which this line was intersecting. And say we finally get to the end of the problem and this is not true, right, there's no point of intersection, then we get something called skewed. Right, and to be a skewed line, again, it means it's not parallel and it's not going to be intersecting. You'll see a visual down here, or I'll hide it, I probably already showed it, I'll try to hide it in that corner there, about how we have two mix-match lines, right? They're not in the same plane, so they're not parallel, and they're going different directions, right? So they never intersect. Okay, so I will leave that there for you guys. I know a long problem. That takes care of lines for us. I will see us in planes, right? We'll go through an explanation of planes. So I will see you soon.